In the previous video, we outlined the three-step numerical solution procedure, which takes us from the real situation that we're trying to model to a numerical solution of that particular system. And there were three steps. And here I want to focus in this video on that third step, which was to solve the linear system of algebraic equations using a big matrix solver technique, direct, iterative, we'll talk more about that, in order to get that numerical solution. And I want to address in this video round-off errors. And then in the next video, we'll talk about the condition number, which tells us something about the system and how amenable it is to being solved numerically. So again, we're focused here on the step 3 of the numerical solution procedure, where we're solving a large system of linear algebraic equations. So an AU is equal to B. A is the coefficient matrix, it's known. B is the right-hand side vector, that's known. And U are the solutions at their particular grid points in the domain where we're approximating the solution. Now, of course, in Chapter 1, we looked at various techniques for solving systems of linear algebraic equations. We had Gauss elimination, using the inverse of A, and so on. But these techniques are only really viable for small to moderate-sized systems of equations. Now we're solving systems of equations that could have thousands or even millions of unknowns, so they're very large, and now we have to emphasize efficiency over ease of use. Now we're going to have a computer doing it, so we don't care about how difficult or complex the algorithm might be. We really just care about getting our solution quickly, efficiently, and accurately. So the methods that we've learned don't carry over. And this is the focus of Chapter 6 in the book, is computational linear algebra. And there are engineers, scientists, applied mathematicians, computer scientists working on these problems every day, is how can we more efficiently solve systems of linear algebraic equations, solve the algebraic eigenproblem, and so forth for very large systems. So one way to evaluate the size of a problem computationally is to look at the number of operations. The operations are additions, subtractions, multiplications, and divisions that are required for the computer to do in order to complete a task. So if you look at the number of operations for typical direct methods for solving systems of linear algebraic equations, they're order n cubed, n here being the number of unknowns. And for typical approaches such as Gaussian elimination, the order of operations is order n cubed. And so n is the number of unknowns. That's the size of the matrix problem I need to solve. And as n goes up, n cubed, of course, goes up very, very quickly. And so we say it doesn't scale well. So as the size of the problem gets bigger, the number of computations become prohibitively large. So what we would like is something that's either order n squared or maybe order n squared log n, something that's less than n cubed. So again, although these methods might be convenient for hand calculations, they're terrible, very inefficient to execute on a computer. Okay, so let's think about the two classes of methods that are available to us to solve large systems of equations on a computer. We have the direct methods, which we've talked about before, such as Gaussian elimination. There's also LU decomposition. And so once again, these are appropriate for small to moderate-sized matrices. Now you notice I'm using relative terms. I'm not giving absolute sizes because this changes over time. As computers and architectures and so forth change, the definition of what's small or moderate or large changes over time. So I'm using relative terms here. Iterative methods are much more appropriate typically because they scale better for very, very large systems of linear algebraic equation. So a direct method, you know what steps to follow, you know the order in which to do the steps, you know how many of those steps you need to do to get the solution. If you use exact arithmetic, you get the exact solution. Iterative methods, each iteration is a set of steps that produces a better approximation than in some initial guess that you started with. So you start with initial guess, you do one iteration, you get a little bit closer to the correct solution, do another iteration, do another iteration. It might take thousands of iterations in order to get to a iteratively converged solution. And so those are iterative methods. You're sacrificing some accuracy because now you do have iterative convergence errors. You're going to truncation the iterative process at some point when you reach a point of diminishing returns in the iteration. And that's the price you pay for getting the solution generally faster than would be the case if you use a direct method for these very large systems. Now, that's just a preview of direct and iterative methods. We'll talk more about the details of those in later videos. But what I want to talk about now is the issue of round-off errors. And round-off errors exist simply because we're storing numbers on digital computers. So this arises whether we're using direct or iterative methods. So this is a common issue in all numerical methods regardless of the type. And there's really two issues. So I've mentioned already the round-off error. Let me discuss that one first, and then we'll also discuss the related issue of numerical stability. Just to introduce it here, we'll talk specifically about it in later videos. So the issue here is for real numbers. These are called floating point numbers on a computer. We call it a floating point number because the decimal point floats, as is the case in scientific notation. So 2.573 times 10 to the 14. So the decimal point floats for a real number. So real number, floating point number means the same thing on a computer. The key is how these numbers are represented on a digital computer. They are not exact. They are done using hexadecimal. I'm not going to get into all the details of that. You can look on Wikipedia or other sources online to learn about the details of how the numbers are actually stored on a computer. But I just want to give you the bottom line. Basically, if you take any interval in the number line, so let's say between 0 and 1, in the continuous case, there's an infinity of values between 0 and 1. But on a digital computer, those are broken up into tiny little discrete chunks. The sizes of those chunks are 2 to the minus 51. Again, I'm not going to get into why that's the number. And that's equal to 4.4 times 10 to the minus 16. So essentially, any line segment is divided up into these little 4.4 times 10 to the minus 16 intervals. Now, this is using double precision. By default, a computer would use single precision, which would be 8 decimal places of accuracy. Double precision gives you 16 decimal places of accuracy. So the key then is these round-off errors are the tiny little errors of this magnitude that occur in every single number that's stored on a computer. So I gave the example in a previous video of 2/3 is not 2/3, it's 0.6666667. But that's true actually for 1 or 0. 0 is not 0 on a computer. It's a tiny little number. It'll be less than 10 to the minus 16, but it's not exactly 0. So all numbers, rational numbers, irrational numbers, all numbers on a computer have these tiny little round-off errors. Now, even though they're tiny, the question is what happens to them. The issue of numerical stability is those little errors, those round-off errors already exist in your solution. What does your algorithm do with those errors? Does it keep the errors small, the round-off errors small, or does it cause them to be magnified and grow? If it's the latter, then your numerical algorithm is unstable. So we want to, of course, develop algorithms that are stable to these round-off errors. So that's a separate issue. We'll talk about that when the need arises in a later video. But the point here is these round-off errors are always present, and we need to think about and be sensitized to what are the effects of these round-off errors.